Of a rhombus or a kite, we have a pretty quick formula. You take the D, the lowercase d stands for diagonal. So in a rhombus or a kite, you have two diagonals. You multiply those two diagonals together, then you multiply them by 1/2, or in other words, you divide them by 2. So a rhombus, the definition of a rhombus is a four-sided shape whose opposite angles are congruent. So this is an example of, you can put an R for rhombus. This one's a kite. The formula is the same for the two, which makes it nice. So this one, again, the diagonal is just from going from one opposite angle to the other. So this red line would be like the length of like D2, we would say. This red line here is D2. Diagonal 1 would be this blue line going from one opposite angle to the other. That's diagonal 1. So you just multiply those two lengths together, split it in half. Same thing for a kite. If you're given your two diagonals, just multiply the two together, then divide by 2. If, let's say, I know this is one question that came up on the homework. If you're given, so you have a kite that looks like this, and all you're given is that this side is 5, and you know that the whole length of like your diagonal 2 is equal to 6. Well, if diagonal 2, so going up and down, is equal to 6, that means that this piece here would have to be equal to 3. And then you can make like a little right triangle and use your Pythagorean theorem to solve for your missing length here. So that's a homework problem when you get to it. We won't really have an example like that in the notes, but you all know how to do it. We all know how to use Pythagorean's theorem. All right, let's do some actual examples now of finding area. To find the area of this would be an example of a rhombus. Your area is equal to your diagonal 1, which we could say is 6, or diagonal 2, which is 8. So it's 1/2 times 6 times 8. So simplifying, 6 times 8 is 48. You divide that by 2, you get 24. So the area of this kite here is 24 meters squared. Nice and quick. And we do our same thing for our friend the kite over here. We have our diagonal 1 is 10. Our diagonal 2 is 7. So our area would be 1/2 of 10 times 7. So 10 times 7 is 70. And then split 70 in half evenly, you get 35. So your area is equal to 35, and then our units would be centimeters squared, since this is an area problem. All right. Quick and easy. We'll get more kind of into the there's just a lot of vocab here that we're going to introduce. And again, this is kind of set up for what we're doing later in the week. We're just going to kind of break it up in parts. So we're going to find angle measures in regular polygons, which is then going to help us find the area later on. When we had our unit on polygons, a regular polygon means that all sides are congruent and all the angle measurements are congruent. So here we have a hexagon, a six-sided shape inscribed inside of a circle. So since it's regular, you could say that all 6 sides are congruent, and since it's regular to all angles will be congruent as well. That's what it means to be a regular polygon. Things to notice in here, breaking down, we can have a radius of a circle. We've talked about that, but you can also have the radius of a polygon. If you notice, we have center P, and center P is both the center of our circle and of our polygon. And if we go to our center, to the point on our polygon, it's a vertice, and our circle is just a point on the outside. So we have P to N. That's the radius of our polygon and also the radius of our circle. So an inscribed figure can share its radius with its polygon. So we can say radius Pn, and we would have another radius in this image as well, Pm, since this goes from the center to a vertex. It also goes from, when we're talking about the circle, it goes from the center to a point on the outside of the circle. And we know that radii are always congruent, so we could say that these two lengths are congruent to each other, which again is it's gonna keep with our setup here. A new vocab word, an apothegm, is the distance, or the distance between the center of your circle, the center of your polygon, to one of the sides. So apothegm PQ goes from the center to a side of your hexagon. It's apothegm. It's like saying a possum with the lisp. Apothegm. And that is, it says kind of more about up here. It's the base, it's the height of an isosceles triangle that goes to our base, and our two radii are legs of our isosceles triangle. So looking, we have a triangle P, M, and N, and we know it's an isosceles because the definition of isosceles is you have at least two congruent legs, and here we have two congruent legs, here and here. But now we have our base of our triangle, so our apothegm is just the height of our isosceles triangle. Since our height goes down and it's perpendicular to our base, it bisects angle P, which is going to be our central angle. And that's what we're going to use in the following examples on the back page to find angle measurements. The fact that our apothegm bisects our angle. And then last piece, angle MPN, so M to P to N, is a central angle, meaning it goes from the center of our circle, or we can talk in this case our polygon, and it has like an arc or a side length that it intercepts. And we can find that the same way we found kind of the sector slices yesterday, by taking how many ever degrees are in a circle, so 360 degrees, and then we divide it by how many like sectors we're making. So in this case, we could have 5 sectors, 1, 2, 3, 4, 5, so 1 for each 5, I didn't count this one, 6, 1 for each side of our hexagon. So in other words, we could really, when we end up finding the area, we're really setting up a problem where we have 6 congruent isosceles triangles, and we know how to find the area of one triangle. So then if we just multiply these, we know are all congruent, we multiply it by 6, we can get the whole area of our polygon. And that's everything that's kind of in the last sentence here, kind of the big point. The measure of your central angle is 360 divided by the number of sides. All right, we're going to put all that into practice now. It seems like a lot. It's really straightforward. We flip to the back. In the diagram, polygon ABCDE is a regular polygon inscribed in circle F, and we're going to find each angle measure. So first thing is good to know how many sides this is. we have 1, 2, 3, 4, 5. So it's a 5-sided shape. So that's the name of it's a pentagon. So 5 sides is a pentagon. And we have just 3 angle measurements to solve for. Our first angle measurement is angle AFB. Should we look going from A to F to B? That's one of our central angles. So you can say AFB is a central angle. So in the last sentence in the box on the other page, so to find the angle measurement of a central angle, you take 360 degrees divided by your number of sides. So the measure of angle AFB is equal to 360 degrees divided by 5, which will get us 72. So the measure of, I'll give you a second to copy it down, but that's the measure of our central angle. So that's this guy right here in red. This is 72 degrees. All right. Next piece. We're going to solve for another angle measure. We're kind of zooming in our picture and like getting smaller and smaller, talking about more specific things. So now we're talking about angle AFG. So that goes from A to F to G. So if I take this isosceles triangle off the diagram and draw it here, I'm going to try to make it a little more isosceles looking. That's better. So we have angle measurement here. This is F, this is G, and this is A. We're just going to we're only looking at that side of the triangle right now. So I'll only label those sides. So we're trying to find whatever this angle is. I will mark it in blue. We're trying to find that angle there, AFG. Right. We're going to use what we got from our last example, because we know that this whole angle altogether, so angle, what was it? We wrote it as AFB. Maybe I should then put the B here so we know where it ends. We know angle AFB is 72 degrees. And I said earlier that this height or our apothem, FG, is going to bisect this angle. So that means these two sides, these two angles have to be congruent to each other. So to split 72 in half evenly, we divide 72 by 2. So the measure of angle AFG is equal to 72 degrees divided by 2, because we're bisecting it. So we get out this blue angle is 36 degrees, which means this one also would have to be 36 degrees. We're going to zoom in again to find our last missing angle. We're looking for angle GAF now. So we said this was A, this was G, this was F. We know this angle is 36 now. We know this is going to have a 90-degree measure. We don't know what angle A is, though. This is what we're trying to find. How we can do that, though, is that our interior angles of a triangle, it's coming back. We haven't done it in a while. It's coming back. I have to add to 180. So you could say 180 minus 90 degrees minus 36 degrees would be equal to, this would be then 54. So that's the measure of this guy here, 54 degrees. So we've gone through and we solved for each. So then using all these, what we're going to go into later on is using these angle measurements to get the side lengths of our triangle. What would be a good exercise to do in the next three-ish minutes? The problem below it is really the exact same, except you have a different sided figure. While I take a sip of my tea here and rest my voice, because it's cracking a lot today. I thought it would be better, but I guess not. Try doing example 3 on your own, and then after a few minutes, I'll put up the answers and you can check how you did. Feel free if you want to work with the person next to you and do it. You can chat about it.
Yeah.